A cold stone wall in Peru fits together so perfectly it seems impossible. This is the lost craftsmanship of the ancient world, a forgotten mastery that built structures to last for thousands of years. By the end of this exploration, you will understand the 7 core principles that made these timeless monuments possible. We will investigate how builders moved mountains of stone without machinery and created concrete stronger than our own. This journey reveals more than historical secrets. It uncovers a complete philosophy for building in harmony with the earth, a mindset we have largely forgotten. What do you think it takes to create something truly meant to last forever? That cold, seamless stone under your fingertips is a question made solid. It asks us what we mean when we say something lasts. Survival is one thing. A pile of rubble in a field has survived, but endurance is something else entirely. It is the active refusal to become a ruin. An enduring structure maintains its integrity, its original purpose, and its capacity to inspire awe century after century after century. The historian John Romer once observed that ancient engineering was at its heart a dialogue with eternity. These builders were not just stacking stones, they were speaking to a future they would never see, and they chose their words with incredible care. This is the heart of the lost craftsmanship we are exploring. It was never just a technical manual on how to cut rock. It was a holistic blend of 3 threads woven tightly together. The first thread was empirical science, a deep, observed understanding of materials and physics, learned through generations of trial and error. The second was refined artistry, a pursuit of perfection in form and alignment that went far beyond mere necessity. And the third, perhaps the most elusive to our modern minds, was a deeply cultural and often ritualistic intention. Building was not separate from worship or community. It was an expression of it. This knowledge was the most precious commodity of its age, and that is precisely why it vanished. It was rarely written down in manuals we could later find. It lived in the hands and the eyes of master builders, passed in silence from teacher to apprentice over a lifetime. When those lineages were broken by time, by conflict, or by cultural change, the dialogue was interrupted. The techniques did not fade. They fell silent, leaving behind only their magnificent, unanswered statements in stone. That silent dialogue with eternity began with a single, fundamental choice, the selection of the very first stone. Before any chisel touched rock or any foundation was dug, the ancient master builder engaged in a profound act of listening. He would walk the quarry, his hands brushing over raw, unworked faces of granite or limestone, not just looking but listening. A gentle tap with a hammer, and the stone would sing back. A clear, ringing tone meant a solid, flawless heart, ideal for bearing immense weight for millennia. A dull thud signaled a hidden fracture, a weakness that would betray the structure in 100 years or 1,000. This was not superstition. It was applied physics, a sonic test for internal integrity passed down through generations of observant craftsmen. This deep, intimate conversation with material is the first lost principle, a mastery of selection and sourcing that we have largely replaced with barcodes and bulk orders. Today, we specify a material by its technical grade, its cost per ton, and its delivery schedule. For the builders of the Parthenon or the pyramids, the origin story of the material was part of its strength. They understood that not all limestone was the same. Stone from the north face of a quarry, which hardened under different seasonal stresses, might be chosen for a cornerstone, while a softer variety from the south face was perfect for intricate carving. Roman engineers did not simply need sand for their legendary concrete. They needed a specific, reactive volcanic ash from the region of Pozzuoli, a material that, when mixed with lime and rubble, would undergo a chemical reaction that actually strengthened in contact with seawater. This concrete did not just resist the ocean, it bonded with it, growing more resilient with each passing century. That is not a generic building supply. That is a geological partner chosen with the precision of a master chef selecting a single, perfect ingredient. This knowledge was hyper-local and painfully earned. It was the cumulative memory of which clay pit produced the most stable bricks after the autumn rains, which forest yielded timber that resisted insects for generations, which iron ore, when smelted in a certain way, produced a metal that would not readily succumb to rust. This was a science written in the landscape itself, learned through generations of trial, observation, and sometimes catastrophic error. The loss of this nuanced, place-based wisdom is one of our greatest disconnects. We can analyze a sample of ancient Roman concrete in a lab and tell you its chemical composition, but we have lost the living tradition that knew exactly which hill to climb to find the ash that would make it magic. We struggle to replicate the vibrant, unfading blues of Maya murals or the self-healing properties of some ancient plasters, not because we lack advanced technology, but because we lack their deep, ancestral intimacy with the very earth they built upon. The first lesson from the stones is this: true endurance is not just about how you build, but begins with what you choose to build with and the profound respect you hold for its inherent nature. The perfect stone was only the beginning of the conversation. Once chosen, it had to be placed within a language far more precise than words, the silent mathematics of the cosmos itself. This brings us to the second lost principle, the geometry of perfection. For the ancient master builder, a straight line was never just a line. It was a ray of sunlight on the morning of the winter solstice. A right angle was not merely a convenient corner, it was a sacred echo of the horizon meeting the sky. Their blueprints were written in the movements of stars and the proportions of the human body, creating structures that were less like buildings and more like three-dimensional prayers. Envision the first light of dawn on a significant day, a priest architect not with complex instruments, but with two simple wooden rods planted in the earth. By sighting along them, he could chart a line across miles of landscape, aligning the central axis of a future temple so that on one specific morning each year, the sun would rise directly along that corridor and flood the inner sanctuary with light. This was not an aesthetic trick, it was a deliberate physical tether between the human realm and the cosmic order. The building became a calendar, a clock, and a statement of belonging in the universe. This alignment was just one expression of a deeper, more pervasive code, sacred geometry. Concepts like the Pythagorean theorem or the golden ratio were not abstract classroom exercises for these cultures. They were observed truths of nature, seen in the spiral of a seashell, the branching of a tree, and the proportions of a human face. To build using these proportions was to make your creation resonate with the same fundamental harmony that governed all life. It was a way of building something that felt inherently right, balanced, and eternally stable because it mirrored the world. The Parthenon in Athens stands as the ultimate testament to this philosophy in stone. At first glance, it appears to be a monument of perfect, rigid lines and right angles, but look closer. Every single line that seems straight is actually a subtle, graceful curve. The columns bulge slightly in the middle and tilt inward. The platform itself arcs upward at the center. This intentional imperfection, called intosis, is a stroke of genius. The builders understood that to our human eyes, truly straight lines over long distances can appear to sag or bend, so they pre-corrected for our own perception. They built the optical illusion of perfection by carefully engineering its opposite. It is a breathtaking display of humility and insight, acknowledging that the building must speak to human experience, not just abstract mathematical ideals. This craftsmanship was a seamless fusion of disciplines we keep separate today: the architect was also the astronomer, the mathematician, and the theologian. The design process was holistic, where the structural integrity, the spiritual function, and the celestial alignment were all parts of a single, indivisible intention. In our modern world, we have fragmented this unity. An engineer ensures the building stands up, a designer makes it look appealing, and an astronomer is someone you visit at a planetarium. We have gained incredible specialization, but we have lost the symphonic worldview that could make a stone temple feel like a living piece of the universe. The stones were now in place and aligned with the heavens, but to create a true monument, they had to be joined together. And for that, the ancients developed a third principle, one that turned separate blocks into a single, unshakable entity. That geometry of perfection needed a physical bond, a way to turn celestial alignment into unshakable earthly reality. This bond was found not in glue, but in gravity and friction, mastered to an almost unbelievable degree. It is the third principle, the art of joinery, engineering without mortar. To understand it, you must step into the dry, high-altitude silence of the Andes and run your hand over an Inca wall in Cusco or at Sacsayhuaman. The sensation is deeply unsettling to a modern mind. Your fingertips meet a cold, seamless surface of polygonal stones, each with dozens of unique, beveled edges, fitting together like a three-dimensional jigsaw puzzle carved by giants. The joints are so tight that, as the saying goes, not even a blade of grass can slip between them. This is not poetic exaggeration. It is a literal, physical fact. These walls were built to last not just for centuries, but through countless earthquakes in one of the most seismically active regions on Earth. Their secret lies in that precise, irregular fit. When the ground shakes, a rigid, mortared wall wants to crack along its straight, uniform joints, but an Inca wall with its interlocking, polygonal stones dances. The blocks shift and settle against each other, absorbing and dissipating the energy, then settle back into place when the tremor passes. They are not fighting the Earth's movement. They are moving with it, a profound lesson in resilience. Achieving this required a kind of craftsmanship we have nearly lost, a tactile, three-dimensional puzzle-solving skill of the highest order. This technique is often called Cyclopean masonry, named for the mythical one-eyed giants, because later people could not conceive of humans moving such stones. The process was one of incredible patience. A master would select a rough block and begin the slow work of dressing it, not to a standard shape, but to fit the unique, negative space of its already placed neighbors. Using stone hammers made of harder rock and possibly tools of bronze alloys, the craftsman would peck away at the surface, creating a slightly convex face. He would then trial fit the block, using a powdered mineral or clay to mark the high points where it touched. Back to the dressing area, grind down those marks and try again. This cycle of fit, mark, and adjust could be repeated dozens, even hundreds of times for a single stone. The goal was not a smooth surface for its own sake, but the creation of multiple points of contact across the entire face of the stone, distributing weight and stress evenly over a vast, complex surface area. This stands in stark contrast to our modern paradigm. Our world is built on the logic of standardization and speed. We pour concrete into uniform molds and bind pre-cut bricks with Portland cement. Our strength comes from steel reinforcement buried within, a hidden skeleton. The ancient strength was all in the skin, in the visible, meticulous fit. Their approach asked a profound question of the material itself. How can you hold your neighbor? Ours asks, what can we pour around you to keep you in place? The lost aspect here is not just the manual skill, though that is immense. It is the mindset, the willingness to spend a lifetime achieving a perfect fit between two rocks that would then be buried in a foundation, never to be seen again. It was a commitment to integrity in the hidden places, a belief that every single interface, seen or unseen, had to be true for the whole to endure. This art of joinery created structures that were monolithic in behavior but not in material. They were assemblies of individuals locked in a permanent, supportive embrace. But what happens when you need to build not just a wall, but a soaring arch or a vast, open space? The ancients had an answer for that too, a fourth principle that allowed stone to defy its own weight and leap across empty space. The art of joinery reached its most awe-inspiring scale on the sun-baked plateau of Giza. Here, the ancient Egyptian builders faced a challenge of a different magnitude, not just fitting stones together, but moving mountains of them into the sky. The construction of the Great Pyramid represents a pinnacle of lost craftsmanship, where physical skill merged with staggering logistical genius. To place over 2 million limestone blocks, each averaging 2.5 tons, required more than brute force. It demanded a symphony of specialized roles, a society organized around a single, monumental intention. Modern engineers like Mark Lehner, through decades of excavation, have revealed not a scene of chaotic oppression, but a highly structured operation. There were quarriers who understood the grain of the stone, haulers who mastered the physics of sledges, and the artisans who prepared the pathways. This was a civilization that had refined the craft of coordination to a fine art. The most discussed mystery is, of course, the method of ascent. How did they lift those colossal blocks to ever-increasing heights? The lost techniques are debated passionately. The theory of a massive, spiraling internal ramp, built within the growing structure itself, suggests a clever use of continuous leverage. Others propose systems of counterweights and levers, a kind of monumental playground seesaw that utilized the very weight of the stones against themselves. Perhaps the most elegant idea involves water. By wetting the sand in front of a stone-laden sledge, experiments have shown friction can be reduced by half, allowing a team of workers to pull a massive block with surprising ease. Each theory points to a deep, intuitive understanding of simple machines and natural forces, a craftsmanship of the mind applied to physical problems. Yet the true craftsmanship extended far beyond movement. Before a single block was set, the builders performed a feat of foundational precision that still baffles surveyors. They leveled the entire 13-acre bedrock foundation to within a fraction of an inch. They likely achieved this using a network of water-filled trenches, creating a perfectly flat plain to build upon, a still sea of stone from which the pyramid would grow. And then there were the casing stones. The pyramid we see today is its skeletal core. Originally, it was sheathed in brilliant white Chora limestone, cut with such exacting precision that the joints were virtually invisible. Each block was polished to a mirror finish, fitted so perfectly that the entire structure would have reflected the sun like a colossal beacon on the horizon. This was not merely decoration. It was a final, breathtaking layer of craftsmanship, a perfect geometric form clad in a seamless, luminous skin. The loss of these casing stones is a tragedy, for they represented the ultimate fusion of engineering and artistry. They took a mountain of stacked rock and turned it into a monument of light. While we can reconstruct the logistics and admire the precision, the methods for placing the final, uppermost stones of the pyramid remain locked in silence. This enduring puzzle is the ultimate testament to the completeness of the loss. We see the achievement, but the hands-on knowledge of those final, dizzying maneuvers is gone. It reminds us that their greatest craft may have been knowing exactly how much knowledge to embed in the stone itself, and how much to carry away in the minds of the builders, leaving us forever in awe of the silent, perfect result. While the pyramids reached for the sun, another civilization mastered a different element entirely, turning the relentless sea into an ally. 2,000 years ago, along the coast of what is now Israel, engineers for Emperor Herod did something that defied all logic of their age. They began pouring a thick, gray slurry directly into the churning Mediterranean. From this watery chaos, they were not building a wall to hold the sea back. They were growing a harbor out of it, creating the magnificent port of Caesarea. Its concrete piers and breakwaters did not simply withstand the saltwater, they thrived in it. 2 millennia later, those submerged blocks are still there, stronger now than the day they were poured, while modern concrete seawalls nearby crumble after mere decades. This is the story of Roman concrete, or opus caementicium, a material so advanced it represents a high watermark of ancient craftsmanship that we still struggle to match. The lost knowledge here is not in moving mountains, but in mixing them. It was a recipe, a precise alchemy of earth and fire and water, whose full instructions vanished into the fog of history. At its heart were 3 simple-sounding ingredients. First, lime, produced by roasting limestone in kilns. Second, a specific type of volcanic ash called pozzolana, named for the town of Pozzuoli near Mount Vesuvius where the best deposits were found. And third, an aggregate, often rubble from older buildings or specific types of stone. The magic, however, was in the proportions and the process. Modern chemists analyzing cores drilled from the Caesarea harbor have discovered something astonishing. Inside the Roman concrete, a rare mineral called aluminous tobermorite has slowly crystallized over centuries. This crystal forms as seawater seeps into the material, reacting with the volcanic ash and lime in a long, slow chemical conversation. Unlike modern Portland cement, which is designed to set quickly and remain inert, Roman concrete was designed to be alive. It was a living material that actually healed its own cracks as new mineral formations filled gaps and strengthened bonds. The craftsmanship extended beyond the recipe to the very act of construction. They would build wooden forms right in the water, then laborers would mix the components, often by foot in large troughs, achieving a specific dough-like consistency. This mixture was then packed into the forms layer by layer. The salt water was not a threat, it was the final, crucial component of the cure, triggering the chemical reactions that would continue for centuries. This knowledge was not held in a single scroll, but in the practiced hands of the foremen who knew the exact feel of the mix, and in the collective memory of an empire that built ports, aqueducts, and domes from Britain to North Africa. Its disappearance was a slow fade, not a sudden break. As the Roman Empire's vast trade networks and centralized projects dwindled, the need for such monumental maritime construction faded. The specialized supply chains for pozzolana broke down. The large, coordinated teams of skilled mixers and form workers disbanded. The deep, empirical understanding of the long cure process, a process that took longer than a single human lifetime to see results, simply stopped being passed down. It became a legend, a story of a lost golden age of building. When engineers in the 18th and 19th centuries sought to recreate hydraulic cement that could set underwater, they were essentially starting from scratch, trying to solve a puzzle the Romans had already mastered 1,000 years prior. Even today, with our electron microscopes and X-ray diffraction, we can identify what is in the concrete, but we cannot perfectly replicate the conditions of its making. We lack the intimate, sensory knowledge of the master mixer who knew the mix was right by its smell and its texture. We struggle to replicate the slow, perfect curing environment of the Mediterranean seabed. The Roman concrete revolution shows us that the highest craftsmanship can be as fluid as mortar in a trough. It was a dynamic, chemical artistry, a partnership with time and the elements that modern industry, with its demand for speed and standardization, has yet to fully rediscover. It poses a humbling question: have we, in our pursuit of building faster and cheaper, forgotten how to build in conversation with time itself? That living concrete, a dialogue with the sea, finds its echo in a very different material, one that breathes and bends. High in the mountains of Japan, a 5-story wooden pagoda sways gently in a typhoon. During a major earthquake, it does not stand rigid and crack. It dances, its entire frame rocking and shuddering like a tree in a storm, and then, when the tremor passes, it settles calmly back into place, completely intact. This is not a paradox, it is the pinnacle of a seventh lost principle, the mastery of flexible joinery, a craftsmanship that understood how to make strength from suppleness. While the Romans tamed the sea with stone, East Asian builders performed a different kind of magic. They learned to build with wood as if it were still alive. At the heart of this system is a deceptively simple secret, the Symbiosis. In the center of a pagoda, running up through its hollow core, is a massive, single trunk of cypress. It is not nailed or bolted to the structure. It hangs loosely, suspended from the rafters at the top, its base resting in a stone socket that allows it to swing freely. During an earthquake, this central pillar becomes a giant, weighted pendulum. As the wooden frame sways in one direction, the heavy Symbiosis swings in the opposite direction, counteracting the motion and dampening the destructive force. It is a brilliant, passive shock absorber conceived centuries before the science of dynamics had a name, but the Symbiosis is only the central dancer. The entire stage is built for movement, thanks to an intricate system of joinery known as the Tokyo, or bracket sets. Picture a complex, three-dimensional puzzle of interlocking wooden arms, stacked like clouds beneath the eaves. Each piece is carved from a single block of wood, with precisely cut slots and protruding tongues, mortises and tenons that fit together with a satisfying wood-on-wood click. No nails, no glue. The entire colossal weight of the roof and its ceramic tiles is transferred down through this elegant lattice of brackets, which distributes the load outward and downward. The genius is in the joints themselves. They are not locked rigid. They are designed to flex, to shift slightly, to absorb energy through friction. When the ground shakes, the whole structure becomes a single, flexible organism, its parts moving in a controlled harmony. The craftsmanship required to achieve this is almost unimaginable. Master carvers, trained for decades, worked from full-scale wooden models and complex oral formulas passed from teacher to apprentice. They had to understand wood not as a uniform building material, but as a living record. They knew which grain orientation could bear the most stress, how the wood would shrink and swell with the seasons, and exactly how to cut a joint so it would tighten under pressure, not loosen. A single miscut by a fraction of an inch could compromise the integrity of the entire bracket set. This knowledge was a language spoken in chisel strokes and the scent of hinoki cypress, a tactile wisdom that lived in the hands and the eyes. Its decline is a slow, quiet story of cultural shift. The demand for such monumental timber temples waned. The generations-long apprenticeship became unsustainable in a faster-paced world. The master carvers who held the three-dimensional plans in their minds grew old without successors. We replaced this intricate, earthquake-resistant wisdom with steel rebar and reinforced concrete, materials we believe we can control absolutely. Yet, in major quakes, modern rigid structures often fail catastrophically. While a 1,000-year-old pagoda simply sways and sighs, its flexible wooden skeleton a testament to a different kind of control, one based on collaboration with natural forces rather than domination over them. The silent question from these wooden towers is profound. Is true resilience found in refusing to move, or in knowing exactly how to yield? The flexible wisdom of wood and the living strength of concrete both point to a deeper truth. These were not inventions born in a laboratory, but insights cultivated in the mind of a single, integrated individual, the master builder. To understand the heart of this lost system, we must meet its most legendary embodiment, a man whose name means he who comes in peace, Imhotep. In the 27th century before the Common Era, he served the pharaoh Djoser not as a mere architect, but as a chancellor, a high priest, and the chief sculptor. He was, in essence, the human convergence of all the principles we have explored. His legacy, the step pyramid at Saqqara, was the world's first colossal stone structure, a daring leap from mudbrick and reed into eternity. Imhotep did not merely design a building. He conceived a new way to build, coordinating the selection of stone, the celestial alignment of the complex, the logistics of a workforce thousands strong, and the profound religious rituals that sanctified each phase of construction. His authority flowed from a complete, unified understanding. He knew the prayers to recite at the quarry to honor the spirit of the mountain, and he also knew the exact angle to cut the stone so it would bear the weight of the pyramid above. This was the core of the craft, knowledge that refused to be compartmentalized. The master builder, or the closed guild that protected these secrets, held a mental model of the entire project, from its spiritual intention to its final, physical detail. He understood material properties not from a textbook, but from the feel of granite under a copper saw and the sound of limestone when struck. He grasped structural physics through the empirical memory of what designs had stood for generations and which had collapsed. He managed labor not through coercion, but through the organized rhythm of a society united by a sacred purpose. Most importantly, he ensured a continuity of vision. From the moment the first foundation trench was blessed to the placement of the final, gleaming capstone, one guiding intelligence was present, making micro-adjustments, solving unforeseen problems, and holding the original, holistic intention sacred. This is the profound fragmentation we live with today. We have divided the unified soul of Imhotep into separate professions. The architect dreams the form. The civil engineer calculates the loads. The project manager oversees the schedule and budget. The contractor executes the plans. Each is a specialist operating in their own domain, often communicating through layers of contracts and digital files. While this specialization allows for incredible complexity, it also creates gaps, places where the deep, intuitive synergy between material, spirit, and structure can fall away. No single person feels the weight of the entire dialogue with eternity. The master builder's authority came from a sacred trust, a cultural sanction that his knowledge served something greater than the project itself. It served the cosmic order, the honor of the king, the memory of the people. Today, authority is derived from credentials, contracts, and liability insurance. The result is often efficiency and innovation, but it is a system less likely to produce a structure that feels like a living prayer in stone. We have gained the ability to build taller, faster, and with more dazzling technology. But in segmenting the roles, we may have lost the path to that older, quieter kind of genius, the kind that could look at a mountain and see not just raw material, but a conversation with the future waiting to be unlocked. That unified vision held in a single mind was a flame, and its only fuel was the next generation. The master builder's greatest work was not the pyramid or the temple, but the apprentice standing silently beside him, watching. This was the true lifeblood of the craft, a river of knowledge that flowed from eye to hand, from gesture to understanding across centuries. It was a system of learning so profound and so fragile that its disappearance explains more about our loss than any forgotten tool. Picture a stone yard in the shadow of a rising Gothic cathedral. A boy of 12 or 13 stands before a rough block of limestone. His master, a man with hands like worn leather, does not hand him a textbook on compressive strength. Instead, he places a chisel in his palm, adjusts his grip with a silent nod, and demonstrates a single, precise strike. A perfect flake of stone falls away. The lesson is not in the lecture, but in the vibration traveling up the boy's arm, in the sound of the impact, in the way the light catches the fresh surface. For the next 10 years, he will repeat this motion 10,000 times. He will learn the feel of grain that fights the chisel versus grain that yields. He will learn to listen to the stone's complaints and its consent. This is tacit knowledge, the deep, wordless wisdom of the body. It is the intuition that tells a carpenter a beam is sound by the tone of his knock, or tells a mason his mortar mix is perfect by its smell and slump. This knowledge cannot be fully captured in words or diagrams. It lives in the muscles, the senses, and the subconscious pattern recognition built over a lifetime of direct experience. The master-apprentice bond was the sole conduit for this river of wisdom. It was a total immersion, a slow seasoning of a human being. The apprentice did not just learn a skill, he absorbed a worldview, a pace, a standard of care where time was a secondary concern to truth. He learned to solve problems not with a pre-approved plan, but with adaptive intelligence. When a foundation settled unevenly or a quarry delivered stone with an unexpected flaw, the master and his team drew upon a deep reservoir of past solutions and intuitive leaps to devise an elegant, on-the-spot fix that the original blueprint never anticipated. The loss of this system is inextricably linked to the rise of the machine and the clock. The Industrial Revolution did not just introduce new tools, it introduced a new philosophy, one that valued standardization, speed, and repeatability above all else. The intricate, time-consuming skills of the hand carver, the stone dresser, and the master joiner were seen as inefficiencies. Why spend a decade training one person to carve a perfect arch when a steam-powered lathe could produce a dozen adequate ones in an afternoon? Construction was broken down into discrete, simple tasks. The holistic craftsman was replaced by the semi-skilled laborer who needed only to follow simplified instructions. The deep, embodied knowledge of materials became irrelevant when those materials were now uniform, factory-made products, bricks of identical dimension, beams of predictable strength, mortar that came pre-mixed in bags. We traded the adaptive genius of the craft for the predictable certainty of the specification. Today, we have something the ancients largely did not: exhaustive documentation. We have digital blueprints with millimeter precision, material safety data sheets, and volumes of building codes. This is a tremendous advantage, allowing for global collaboration and incredible structural complexity. Yet, we often lack the deeper layer, the on-site wisdom that knows when the blueprint is wrong for the specific patch of earth it sits upon. We have replaced the master's discerning eye with the inspector's checklist. The question this forces upon us is uncomfortable. Have we, in our pursuit of perfect, replicable information, accidentally orphaned a deeper kind of knowing? Can 1,000 pages of technical specifications ever truly contain the lesson held in a single, well-placed strike of a master's hammer? The master's hammer was only as wise as the hand that held it, and that hand was guided by tools of breathtaking simplicity. A polished river stone, a length of knotted cord, a wooden frame with a dangling string, these were the instruments that built empires. The true marvel is not that they built so much with so little, but that they saw so much with such humble extensions of their own senses. The craftsmanship lived in the intimate calibration between the tool, the material, and the human eye. An Egyptian architect aligning a temple used a merkit, a simple forked sight made of wood, to track the passage of specific stars across a notched bar. With this, he could lay out true north with an accuracy that still amazes astronomers. The tool itself was basic, but the knowledge of the night sky it channeled was profound. Similarly, a Roman surveyor, tasked with laying a road straight across mountains and valleys, relied on a groma. This was a cross-shaped instrument with plumb bobs hanging from each arm. By sighting along the aligned strings, he could project perfectly perpendicular lines across miles of uneven terrain. The tool did not think. The surveyor did, interpreting the sway of the bobs in the wind, compensating for the slope of the ground, holding the vision of that straight line in his mind's eye. This deep, interpretive relationship is what we have altered. Our tools now do the interpreting for us. A modern laser level projects a perfectly straight, self-correcting line. A digital theodolite gives a numerical readout to 1,000th of a degree. The feedback loop between the craftsman and the task is mediated by a screen and a microchip. The intuition that came from feeling a structure go out of true, from seeing a plumb bob's subtle drift, is replaced by trusting a digital display. The Inca stonemason's most prized tool for testing a fit was often just a flat, polished stone called a ñusta. He would rub it over the surface of a newly dressed block. The pattern of wear on the ñusta, or the transfer of colored dust, showed him the high spots invisible to the eye. He was not measuring in millimeters, he was reading a story of contact written in stone dust. His mastery was in translating that story into another minute adjustment with his hammer. This process embedded knowledge directly into his hands. The rhythm of his strikes, the angle of his chisel, the pressure of his palm on the ñusta, all became a physical memory. The shift from hand tools to power tools represents more than an increase in speed. It represents a fundamental change in this somatic learning. A vibrating saw cuts quickly, but its noise and power mask the subtle feedback of the material. You cannot hear the grain of the wood change or feel the stone's resistance through the handle in the same way. The connection is muted. We have gained incredible precision and efficiency, but we have placed a layer of technological abstraction between the builder's intuition and the soul of the material. The ancient tools asked for partnership. They required the craftsman to bring his full attention, his learned judgment, to complete the circuit. Our advanced tools often ask only for correct operation. They deliver phenomenal results, but they do not necessarily make the one who uses them more deeply understand why a wall stands or a joint endures. The final, silent partner in all this work was not a tool at all, but a living, breathing system of belief that turned labor into a sacred act. The master's tools were extensions of his senses, but his senses were first trained by the world itself. This leads us to a fourth principle, perhaps the most quietly profound of all: environmental symbiosis. The ancient builder did not see a landscape as a blank slate to be conquered, but as a living partner with its own logic, gifts, and challenges. His craft was to listen to that place and build a response directly into the stone. Nowhere is this dialogue more breathtaking than in the silent, sun-baked cliffs of Mesa Verde. Here, around 800 years ago, ancestral Puebloan builders did not construct on the mesa top. They built within it. They sought out vast, south-facing sandstone alcoves, natural shelters carved by millennia of water and wind. Into these curved, protective arms, they fitted entire villages of multi-story dwellings, their back walls merging seamlessly with the living rock. The choice was not merely defensive, though it offered protection. It was a masterstroke of environmental engineering. The massive sandstone overhang acted as a giant thermal mass, absorbing the sun's heat during the day and slowly releasing it through the cool desert night, moderating extreme temperatures. In summer, it provided deep shade, while in winter, the low-angled sun could still penetrate to warm the dwellings. The alcove itself often channeled precious seeping groundwater, which could be carefully collected. This was not building on the land, it was a form of architectural grafting, where the human structure became an outgrowth of the geological one. This deep site analysis was a universal hallmark of the lost craft. Before a single foundation stone was laid, the master builder was a student of the microclimate. He observed the path of the sun through the seasons, not just for alignment but for comfort. In ancient Greece, houses were often oriented to capture the low winter sun for warmth, while their thick walls and shaded courtyards provided cool retreats in the summer heat. He charted the prevailing winds. In the arid plains of Persia, this understanding gave birth to the windcatcher, or badir, a towering chimney-like structure that captured even the faintest breeze, funneled it down over cool water channels, and circulated refreshing air throughout the home without a single watt of electricity. He studied the flow of water across the terrain, designing drainage systems that channeled rainfall away from foundations and into cisterns, turning a potential threat into a vital resource. He learned the seismic personality of the land, as the builders of Istanbul's Hagia Sophia did, designing a dome that could flex and sway with the Earth's movements. This was not an add-on, not a feature called sustainability. It was the foundational logic of the design itself. The building's form emerged from a conversation with sun, wind, water, and stone. The loss of this principle is written across our modern skylines. We have perfected the universal, climate-controlled box. We now take identical glass towers, steel frames, and concrete shells and plop them down in the desert, the rainforest, and the tundra. The environment is then treated as an enemy to be battled at tremendous energy cost. We scorch fossil fuels to cool buildings in Dubai and burn them again to heat identical structures in Oslo. Our technological separation has allowed us to ignore the local logic of place, but the consequence is a profound inefficiency and a disconnect from the very world we inhabit. The ancient craftsman had no such luxury. His success depended on his humility, his willingness to learn the language of a specific hillside or valley and to build in fluent reply. His work asks us a question we are only now urgently relearning. What does this place want to be? The final, silent partner in all this work was not a tool at all, but a living, breathing system of belief. In the dust and heat of a Mesopotamian plain, 3,000 years before our time, a community gathers. The air is thick with the smell of damp earth and incense. A priest-king approaches a deep, rectangular trench, the prepared foundation for a new temple. He does not simply order the first stone lowered. He raises a vessel and pours a libation of honey, milk, and wine into the earth, a gift to the gods below. Chants rise, calling upon divine patrons to accept this offering and bless the work. Only then is the massive cornerstone, already carved with prayers, settled into place. This was not a groundbreaking ceremony as we understand it. It was a literal act of consecration, a fusion of physical labor and spiritual covenant. For the ancient world, the act of building was rarely a secular project. It was a sacred ritual, and the craftsmanship itself was a form of devotion. Every measurement was a recitation of cosmic order. Every orientation was an alignment with celestial powers. The choice of cedar from a distant mountain was not just about durability. It was about bringing a piece of a sacred forest into the heart of the city. This profound context transformed the work. When you believe you are building the dwelling place of a god, or a vessel for your ancestors, or a bridge between heaven and earth, your standard of care shifts fundamentally. Perfection is no longer a matter of pride or even utility. It becomes a spiritual obligation. A slightly uneven joint is not just a cosmetic flaw, it is an insult to the deity you are trying to honor. A misaligned wall that fails to catch the solstice sunrise is a broken promise to the community and the cosmos. This mindset infused the work with a patience we struggle to comprehend. Time became a secondary currency, spent lavishly in pursuit of a truth that transcended the lifespan of any individual builder. The drive was for eternal quality because the structure was meant to serve an eternal purpose, to stand as a testament to faith and cultural identity for as long as the world turned. This is the dimension most absent from our modern construction paradigm. We build within a framework of budgets, timelines, and profit margins. These are not inherently negative forces, but they are fundamentally different motivators. They prioritize efficiency over eternity, cost-benefit analysis over cosmic harmony. The question is not whether a joint is perfect in the eyes of the gods, but whether it meets code and can be completed by the third quarter deadline. We have secularized the act of building, and in doing so, we may have unintentionally released ourselves from the very pressures that demanded transcendent quality. The loss is not of skill alone, but of sacred intention. When craftsmanship is a devotional act, the builder is accountable to something greater than a client or a contract. He is accountable to a story, a people, and a legacy. That accountability is what could compel a worker to spend a month perfecting a single stone that would be buried forever, simply because he knew it had to be right. It is what could inspire a community to haul blocks for generations, not for wages, but for the collective honor of raising a beacon to their gods. This sacred context did not slow progress, it redefined its goal. The purpose was not just to create shelter, but to create meaning, to etch a culture's highest ideals into the landscape itself. In a world where we often build for disposable use, with planned obsolescence in the back of our minds, the ancient approach feels almost alien. Their buildings were love letters to the future, written in a language of stone and alignment, and they believed, with every libation poured and every prayer chanted, that the future would be listening. This leaves us with a quiet, unsettling thought. If we no longer build for the gods or for eternity, what or who are we building for? And does that answer explain why so much of what we create feels so temporary? That sacred intention to build for eternity demanded more than faith, it demanded proof. The path to perfection was not a straight line drawn by a divine hand, but a slow, winding road paved with the rubble of failures. This is the fifth principle, the power of empirical iteration, a relentless process of learning from collapse. To see this in action, you must walk through the ruins of ancient Greece, not as a tourist, but as a forensic engineer in time. Begin at the Temple of Hera at Olympia, one of the earliest large stone temples from the Archaic period. Its columns are massive, squat, and built from drums stacked with a simple, heavy precision. They look powerful, but they are rigid. Now travel forward a century in your mind to the Parthenon in Athens, the pinnacle of the classical era. Its columns are taller, more slender, and elegantly tapered. They possess that subtle curve, the entoses we discussed, and they stand with a lighter, more confident grace. This evolution was not merely an aesthetic trend. It was a direct response to the Earth's violent lessons. Greece sits on a tectonic crossroads, a land regularly shaken by powerful earthquakes. Each tremor was a brutal, unvarnished test of every architectural assumption. When an early temple collapsed, the community did not see it as a divine curse alone. The master builders and stonemasons would have surveyed the wreckage with a practical, analytical eye. They would have seen how the rigid, bulky columns of the archaic style snapped at their joints or toppled as monolithic units. They observed that straight lines became weaknesses under dynamic, lateral stress. From this carnage, a slow realization emerged: rigidity is a vulnerability. The solution was not to build thicker, heavier walls, but to build smarter, more flexible ones. Over generations, they refined their designs based on this empirical feedback. They began tapering columns, making them slightly wider at the base and narrower at the top, improving stability. They introduced entoses, which not only corrected optical illusions but also created a column that was stronger in its central third, the area of greatest bending stress. They perfected the joinery between column drums, using precise wooden dowels that allowed for minute movement without total failure. Each new temple was a hypothesis, a living experiment that would stand for decades or centuries until the next great quake delivered its verdict. The knowledge was cumulative, written not in scrolls, but in the evolving language of stone itself. This process reveals a cornerstone of the lost craftsmanship. It was profoundly iterative and deeply patient. Innovation was measured not in years but in lifetimes. A master builder inherited the collective memory of successes and failures from his grandfather's time, applied his own refinements, and then bequeathed a new, slightly more resilient standard to his apprentice. The entire craft was a slow-motion conversation with the forces of nature, where each collapse was a question, and the next structure was the refined answer. This stands in stark contrast to the timescale of modern engineering. Our projects are magnificent, built with materials and calculations the ancients could never dream of. Yet they are almost always conceived, constructed, and evaluated within a single human lifespan, or even a single corporate fiscal cycle. We build a skyscraper and declare it a success if it stands for 50 years. But what about 500 or 5,000? We lack the multi-generational feedback loop for ultra-long-term performance. Our concrete is tested for decades, not centuries. Our steel alloys are evaluated for corrosion over 50 years, not a millennium. When a modern structure does eventually fail, the lessons are studied, but the original architects, engineers, and builders are long gone, and the corporate entity that built it may have dissolved. The institutional memory is fragmented, stored in reports that may or may not be consulted a century later. The ancient system, for all its technological simplicity, was elegantly adapted to the very long game. The builder was also the maintainer, the observer, and the teacher for the next generation who would one day repair or rebuild what he had made. His name might be forgotten, but his lesson, embedded in the surviving stones, was not. This principle forces us to ask a humbling question: can true resilience, the kind that speaks across millennia, ever be designed in a single lifetime? Or does it require the patient, collective memory of generations who are willing to listen, even to the devastating lessons of the fallen? A 50-ton stone giant stares blankly across a remote island, its journey from quarry to coast a silent epic of human ingenuity. The true marvel of the Easter Island moai, or the colossal trilithon stones at Baalbek, is not their final Chinese letter posture, but the unimaginable motion that brought them there. This represents the seventh lost principle, the mastery of megalithic logistics, a craft that turned impossible weight into managed momentum. It was a symphony of applied physics, where brute force was the last resort and cleverness was the true engine. The fundamental challenge was friction, and their solutions were elegantly simple. For moving a moai, the most supported theory involves a rocking, walking motion. Teams of workers would use ropes to tilt the statue forward onto one edge, then swing it to the other side, inching it along a prepared path. This converted a sliding drag into a series of manageable lifts, a brilliant manipulation of a center of gravity. On the plains of Lebanon, for the Baalbek stones weighing over 800 tons, the approach was different. Evidence suggests the use of massive wooden sledges, not dragged raw across the earth, but gliding on a track lubricated with a slick slurry of water and clay. This could reduce the effective pulling force required by more than half, transforming an impossible haul into a difficult but achievable communal effort. The other ubiquitous tool was the humble log, used as both roller and pivot. By placing a sledge atop a continuous track of greased logs, workers could create a primitive but highly effective conveyor belt. As the sledge moved forward, logs from the back were retrieved and placed in front, allowing a relatively small team to keep a monstrous weight in motion with a steady, rhythmic push. The craftsmanship was in the coordination, the precise timing of placing and retrieving those logs without losing momentum or crushing a hand. This was not chaotic heaving. It was a choreographed performance of levers, ropes, and human rhythm. The organization of labor was itself a high art, a lost science of crowd management. Historical accounts from other cultures, like those moving obelisks in Egypt, describe a foreman beating time on a drum or blowing a whistle. Each pull on the ropes was a collective heave in unison, timed to a work song that set the pace and built morale. This sonic coordination turned 1,000 individual pulls into a single, powerful pulse of force. It was psychological engineering using rhythm and shared purpose to align muscle and will. The specific techniques for maneuvering these objects over miles of rough terrain or raising them onto vertical platforms remain partially in the realm of educated speculation. How did they pivot a multi-ton block into a precise socket without shattering its edges? How did they navigate a sloping path without letting gravity take catastrophic control? The answers likely involved temporary earthen ramps, complex systems of counterweights and levers using frames, and an intimate, tactile understanding of how stone reacts to stress. This knowledge was not held in formal equations, but in oral tradition and embodied practice. A master mover knew the sound of a rope under safe tension versus one about to snap. He could feel through his feet the moment a sledge began to bind on its track. He could judge the exact moisture content of the clay lubricant by its sheen. This was a holistic, Chinese letter intelligence that has no direct modern equivalent. We have cranes and flatbed trucks that make such feats trivial for machinery, but we have largely lost the communal, physics-based artistry of moving the unmovable with nothing but wood, rope, water, and synchronized human effort. It was a craft that asked not for stronger materials, but for smarter relationships between force, friction, and fellowship. The silent giants they left behind are not just statues or temple walls. They are frozen evidence of a moment when an entire community became, quite literally, a single thinking machine. That final, graceful curve on a Greek column was not merely for the eye. It was a direct response to the memory of past earthquakes, a beautiful solution born from a brutal lesson. This reveals a deeper truth about the ancient world's approach, one where aesthetics were never an afterthought, but the very face of durability. Walk through the ruins of Angkor Wat as the first monsoon rain begins to fall. Watch as water cascades down the towering spires, not in a chaotic deluge, but in a controlled, artistic flow. Every nymph carving, every intricate lotus relief, is also a meticulously placed gutter. The elaborate demon faces are not just mythological guardians. They are ornate spouts, channeling torrents of water away from the fragile sandstone joints below. Here, decoration is drainage, ornament is preservation. The beauty of the structure is inseparable from its battle against time and the elements. This is the aesthetics of durability, a principle where visual splendor emerged from structural honesty. The form was a truthful expression of the function, and in that truth, a profound and enduring beauty was found. Consider the fluting on a classical Greek column. Those elegant vertical grooves do more than catch the light and create a sense of rhythm. They actually reduce the visual weight of the massive stone cylinder, making it appear more graceful and alive. But they also serve a physical purpose. The grooves create a series of ridges that can better resist the propagation of cracks, much like the corrugation in cardboard adds strength. The aesthetic choice directly enhanced the material's resilience. In the soaring heights of a Gothic cathedral, this unity reaches its zenith. The flying buttress, that iconic stone arm leaping away from the wall, is the purest poetry of structural necessity. It was an engineering breakthrough, a way to redirect the crushing weight of the vaulted ceiling outward, allowing walls to be filled with vast, luminous stained glass. Yet the architects did not hide this innovation. They celebrated it, sculpting these buttresses into arches of breathtaking lightness, often adorned with pinnacles and tracery. The buttress was not an ugly support to be concealed. It was the skeleton made visible, transformed into the building's most dramatic artistic feature. This holistic philosophy created a powerful, self-reinforcing cycle of care, because the beauty of the building was woven into its structural logic. Preserving one meant preserving the other. A community maintaining the glorious stained glass windows of their cathedral was, by necessity, also inspecting and repairing the stonework of the buttresses that held those windows in place. The artistic value and the structural value were a single, sacred trust. This stands in contrast to a common modern divide, where architecture and engineering can become separate conversations. Today, an architect might envision a stunning, cantilevered form, a shape that challenges gravity. An engineer is then tasked with making it stand, often by hiding a forest of steel beams and complex reinforcements within the walls, a truth cloaked behind a facade. Conversely, purely functional elements like ventilation ducts or seismic joints are often treated as visual blights to be boxed away, rather than design opportunities. This separation can create fragility. A decorative cladding system chosen solely for its appearance might trap moisture against the building's real skin, leading to decay unseen until it is too late. The ancient approach asked a different question: how can the need for strength and the desire for beauty become the same answer? Their legacy suggests that the most enduring beauty is not applied to a structure, but emerges from its honest bones, a lesson written in stone, water, and light for any future builder willing to read it. That seamless fusion of beauty and strength was a gift not just for the present, but a deliberate inheritance for the future. The intricate carvings of Angkor Wat were more than art. They were a detailed maintenance manual written in stone. Every demon-faced spout, every decorative lotus that channeled monsoon rains, was designed with a clear expectation. Someone would need to clear the leaves from it next year, and the year after that for centuries to come. This reveals the sixth lost principle: maintenance as a core design philosophy. Ancient builders did not see their work as finished at the dedication ceremony. They saw it as the beginning of a relationship between the structure and a lineage of future caretakers. Their craftsmanship included designing for its own future care. They built in access. In the vast Roman aqueducts that marched across continents, regular inspection shafts and accessible channel interiors were standard features. The builders knew that silt would accumulate, that mortar would need patching, that a vigilant eye was the only thing keeping the water flowing. They designed for graceful degradation. Many ancient plaster recipes included a sacrificial outer layer, a softer coat meant to weather and erode slowly, protecting the harder, more vital substrate beneath. When it eventually wore thin, the repair was simple. A new layer could be applied over the old, a cycle of renewal built into the very skin of the building. Most profoundly, they designed for the human hand. Components were sized and placed so that a person, with simple tools and local materials, could reach, understand, and repair them. A loose stone in an Inca wall could be identified and reset. A worn timber in a Japanese pagoda's bracket set could be replicated and swapped out by a trained carpenter using the same joinery techniques. The structure was not a sealed black box. It was an open system meant to be understood and tended. This embedded a mindset of long-term stewardship. The original builders were the first link in a chain of custodians they would never meet. They built with the humility to acknowledge that their work would not remain perfect, but with the confidence that it could be made whole again. This stands in quiet contrast to a modern tendency toward the build and forget model, or worse, design so complex and sealed that they defy simple repair. Consider a contemporary glass curtain wall on a skyscraper. It is a marvel of engineering, but when its sealed, insulating unit fails or its complex anchoring system corrodes, the solution is rarely a simple patch. It often requires a team of specialists with proprietary parts, massive scaffolding, and enormous cost. The building becomes a passive object to be serviced by external, expensive expertise, rather than an active participant in its own longevity. The loss of this maintenance-first principle is not merely technical, it is cultural. It reflects a shift in our relationship with time and ownership. When we build with an expectation of replacement in 50 years, we invest less in designing for 100 years of care. We prioritize initial cost and speed over long-term resilience and repairability. The ancient approach asks a different question of a design. Not just how will this stand up, but how will this be taken care of? The silent, enduring presence of so many ancient monuments is not just a testament to how well they were built, but to how wisely they were built to be maintained. Their survival is a conversation across time, where the foresight of the first builder is answered by the care of countless unknown hands that followed. It suggests that the most durable material in any structure is not stone or concrete. but the ingrained intention for it to be cherished, fixed, and passed on. The most sophisticated engineering principles of their age were never meant to be read. This is the great paradox of the lost craftsmanship, a silence in the historical record that speaks volumes. We have their monumental answers in stone, but we are missing their working questions, the how-to manuals that should logically accompany such feats. The reason is not an accident of time, but a deliberate feature of the system itself. This knowledge was often proprietary, a fiercely guarded trade secret. In societies organized around guilds or family lineages, the techniques for mixing the perfect mortar or aligning a temple were the source of livelihood, status, and power. To write it down for anyone to copy would be to surrender that advantage. This craft was their intellectual property, protected not by patents but by silence and ritual. The master passed it to the chosen apprentice in a sacred trust, ensuring control over who could build the most important structures for king and community. This created a living library, but one that could burn down in a single generation. Beyond secrecy, there was a deeper, more fundamental barrier, the nature of the knowledge itself. So much of it was tacit, a wisdom of the hands. How do you describe in words the exact sound of a good limestone block, or the precise feel of mortar that has reached the perfect consistency? How do you write down the intuitive judgment for shaving one more sliver from a stone to achieve a friction fit? These were sensory and motor skills learned through endless repetition and correction under a watchful eye. Translating that embodied intelligence into a linear text is like trying to describe the taste of honey to someone who has never eaten it. The instructions would be hopelessly incomplete. The true manual was the apprenticeship itself, the 10,000 hours of doing, failing, and doing again until the knowledge moved from the conscious mind into the muscles and the instincts. In many of these cultures, the craft was also shrouded in the sacred or the royal. The knowledge of how to align a pyramid with the stars or how to consecrate a temple foundation was not mere technical data, it was ritual power. It belonged to the priest architect or the royal engineer, and its dissemination was controlled as a matter of state security or religious sanctity. To share it widely would dilute its potency and its association with divine or kingly authority. What written records did exist often took forms destined to vanish. Scrolls of papyrus, bundles of palm leaves, or wax tablets housed in libraries that were themselves vulnerable to fire, flood, or the simple decay of organic materials. When the great library of Alexandria suffered damage, it was not just poems and histories that were lost, but potentially countless technical scrolls on engineering, architecture, and material science, the practical textbooks of the ancient world. This reliance on a fragile chain of human transmission made the entire edifice of craftsmanship uniquely vulnerable. It could survive the collapse of a single building, but not the collapse of a social order. When war, famine, or profound cultural change disrupted societies, the unbroken line from master to apprentice was severed, the guild halls emptied, the sacred schools closed. The elders who held the secrets in their minds passed on without someone to receive them. The knowledge did not fade slowly, it often snapped abruptly, leaving behind the magnificent, silent structures as the only testament to what had once been known. This is why the gaps in our understanding feel so absolute. We are not looking for a lost book we might one day find in a tomb. We are listening for an echo of a conversation that stopped speaking centuries ago, a dialogue between teacher and student that ended mid-sentence, leaving the stones themselves as the only remaining word. That silent conversation between teacher and student ended centuries ago, but we have not stopped trying to listen in. In recent decades, a new kind of dialogue has begun, one conducted with cameras rolling and grant proposals funded. Teams of modern archaeologists, engineers, and skilled masons have taken on a fascinating, humbling challenge to reconstruct ancient techniques not on paper, but in physical reality, using only the tools and methods available at the time. Their goal is not to build a new monument, but to rebuild a lost understanding, one stone at a time. These modern replication projects are journeys into a forgotten mindset, and they reveal as much about our own limitations as they do about ancient genius. Consider a team working on the Giza Plateau, attempting to move and place a 2-ton limestone block using only ropes, wooden sledges, and a crew of volunteers. The theory is clear: wet the sand to reduce friction, pull in unison, use wooden levers for positioning. On paper, it is elegant and simple. In practice, it is a lesson in controlled chaos. The first hurdle is time, a resource we value very differently. What a dedicated ancient crew might accomplish in a day of rhythmic, practiced labor can take a modern team a week of trial, error, and recalibration. The second, more profound hurdle is the feel for materials. A modern engineer knows the coefficient of friction for wood on sand. An ancient foreman knew the exact amount of water to pour to create the perfect slick slurry without turning the path into a muddy trench that would bog down the sledge. That knowledge was not calculated, it was sensed. It lived in the glance at the sky to judge the day's heat, in the feel of the sand underfoot, in the collective memory of 100 previous moves. The modern team, for all its technology and historical research, is essentially guessing, relearning through slow, painful iteration what was once second nature. Successes in these experiments are hard-won and deeply revealing. One team successfully demonstrated how a small crew could pivot a multi-ton obelisk using a fulcrum and a sandbox, a clever method long hypothesized. Another, working with Roman concrete, has finally decoded the basic chemical recipe, identifying the crucial volcanic ash and the mixing process. We can now make a material that closely resembles the ancient one in a laboratory setting. Yet here lies the stumbling block, the difference between resemblance and replication. Modern-made Roman concrete, while strong, does not always exhibit the same self-healing properties, the same gradual strengthening over centuries in seawater. The missing ingredient may not be a physical component, but a temporal one, the specific conditions of a long, slow cure in the Mediterranean environment, or perhaps a subtle mixing technique born from a lifetime of experience that no written source ever thought to record. These projects highlight the chasm between theoretical understanding and master-level execution. We have successfully decoded the what, the list of ingredients, and the broad strokes of the method. But the nuanced how, the tactile wisdom, the ingrained sense of timing and proportion, the seamless integration of spiritual ritual with physical labor that transformed a construction site into a sacred space, this true craftsmanship remains just out of reach. It is like having the sheet music for a complex symphony but lacking the lifetime of training to understand the phrasing, the emotion, the breath that turns notes on a page into a living, stirring performance. The modern replicator, armed with data but divorced from the cultural cradle that produced the knowledge, is trying to play the symphony by reading the instructions aloud. The sound is recognizable, but the soul of the music is absent. These experiments, for all their stumbling blocks, are not failures. They are the most honest form of respect. They prove that these ancient achievements were not the work of aliens or myths, but of human intelligence of the highest order. More importantly, they teach us that this intelligence was holistic. It was not just brains in a jar, but knowledge embedded in the hands, in the community, and in a relationship with the world that we have since partitioned into separate, specialized boxes. The greatest lesson from these dusty, exhausting modern trials may be a quiet one, that some forms of knowing cannot be rushed, reverse-engineered, or fully captured in a report. They can only be lived, and that requires a kind of time and a unity of purpose we have yet to relearn. That modern attempt to rebuild the ancient way reveals a profound truth: we are not starting from scratch. Our contemporary world of steel and glass is, in many ways, a direct descendant of those first stone conversations. The legacy of this lost craftsmanship is not a ghost, but a foundation, quite literally built into the structures all around us. Look up at any grand train station or Capitol building with its vaulted ceilings. That soaring space is made possible by the Roman arch, a principle perfected 2,000 years ago that redirects weight outward and downward, allowing for openings in solid walls. The evolution of that arch into the dome gave us spaces like the Pantheon, a feat of concrete engineering that inspired every monumental rotunda that followed. Even the most basic concept of digging a deep, stable foundation, of creating a level plane from which to build upward, is a direct inheritance from the pyramid builders and their meticulous water trenches. Our modern skyscrapers may root themselves in bedrock with steel pilings, but the fundamental idea of preparing the earth to receive a load is an ancient one. Perhaps the most elegant modern echo is found in how we protect buildings from earthquakes, the principle of seismic base isolation, where a structure is placed on flexible bearings that allow it to sway independently of the shaking ground, feels like a high-tech revelation. Yet its spiritual ancestor is the Japanese pagoda with its suspended central pillar, the Shinbashira, acting as a giant pendulum to dampen force. The physics are more calculated now, with synthetic rubber and lead cores, but the core insight is the same. Sometimes, to survive a force, you must move with it, not against it. We have inherited their brilliant solutions to physical problems: the arch, the dome, the foundation, the shock-absorbing joint. We have analyzed, mathematized, and scaled these principles to heights they never dreamed of. But the inheritance is curiously selective. We took the technical skeleton but often left behind the cultural flesh that gave it meaning. The key difference lies in the underlying philosophy. Ancient craftsmanship, by necessity, sought a deep harmony with natural limits. It asked, how can we use this local stone, this specific timber, this understanding of the sun and wind, to create something permanent within the world as it is? Their innovation was about perfecting a dialogue with existing constraints. Modern engineering, empowered by global supply chains and synthetic materials, frequently operates on a philosophy of transformation. It asks, how can we overcome this site's limitations? How can we reshape this material to our will? We pour concrete to create land where there is water, suspend glass curtains in freezing climates, and light interiors with artificial suns. This is not a criticism, it is an observation of a different relationship with nature, one of tremendous power and possibility. Yet this shift explains the haunting feeling when we stand before an Inca wall or a Roman harbor. We recognize the intelligence, but we sense the absence of that other dimension, the sacred intention, the patience of the multi-generational feedback loop, the deep local knowledge that treated material as a partner. Our legacy from the ancient builders is therefore a mixed one. We possess an amplified version of their technical genius, allowing us to perform miracles of construction every day. But we are still relearning the softer, deeper wisdom that ensured those miracles would gently endure for millennia. Their true gift was a reminder that every structure tells two stories, one of how it stands up, and another, quieter story of why it was worth standing up for in the first place. The silent stones hold another story, one not of celestial alignment or perfect joints, but of human hands. To truly understand the legacy of these structures, we must also listen for the echoes of the society that built them, a reality often far removed from our romantic visions. The breathtaking precision of a pyramid's casing stones, the seamless fit of an Inca wall, these triumphs of design and supervision existed within complex and frequently harsh social frameworks. The master builder's genius was often enabled by the labor of countless others, individuals whose participation was not always a matter of choice. Historical research suggests that many of the world's most enduring monuments were raised by systems of coerced labor, state-mandated service, or slavery. The stones were moved by conscripted peasants fulfilling a tax obligation to their king, by captured prisoners of war, or by individuals bound in servitude. This is not to diminish the skill present on those sites, for there was skill at every level, from the overseer who understood logistics to the laborer who knew exactly how to pull a rope in rhythm. But it is to add a necessary, sobering layer to the narrative. The pursuit of eternity for a pharaoh, an emperor, or a god-king was frequently built upon a foundation of profound social inequality and human hardship. This creates a challenging ethical tension for us as modern observers. We can stand in awe of the engineering, the artistry, the sheer will to create something permanent, while simultaneously acknowledging the steep and often painful cost paid for that permanence. It prompts a difficult but essential question. Can we separate the beauty and ingenuity of the artifact from the conditions of its creation? The craftsmanship in the design is undeniable, a testament to human intellect. Yet the craftsmanship in the execution is intertwined with the societal values of its time, values that often placed collective glory or divine mandate above individual liberty. This duality forces us to reflect on the relationship between a society's deepest beliefs and the physical legacy it leaves behind. A culture that believed its ruler was a god on earth would marshal its entire population, willingly or not, to build his house for eternity. A society structured around rigid hierarchies saw the mobilization of massive workforces as a natural expression of power and order. The enduring monument, then, becomes a frozen snapshot of that society's priorities, its capabilities, and its ethical blind spots. Our admiration for the technical achievement need not be an endorsement of the social system that produced it. Instead, it can become a more nuanced form of respect, one that honors the ingenuity of the human mind while holding space for the memory of human struggle. It reminds us that the stones do not just speak of how something was built, but also for whom and by whom. This critical perspective does not tarnish the wonder, it deepens it, transforming a simple tale of ancient genius into a more complete and more human story. It suggests that the most enduring lessons from the past are not just about how to make things last, but also about what we choose to sacrifice in the name of permanence, and who ultimately bears the weight of our ambitions for eternity. The stones speak of weight and alignment, but sometimes they were also designed to sing. A seventh principle of the lost craftsmanship reveals itself not in what you see, but in what you hear and feel, a mastery of acoustic and sensory engineering. This was the art of building environments that actively shaped human experience through sound, light, and shadow, turning architecture into a kind of instrument. Walk into the Whispering Gallery of St. Paul's Cathedral in London. A friend stands dozens of meters away, facing the wall, and murmurs a secret. The sound travels along the curved stone surface, carried with impossible clarity directly to your ear as if they were whispering right beside you. This is not an accident, it is physics sculpted into form, a demonstration of how geometry can conduct sound like a wire. This awareness was ancient. The open-air theaters of Greece and Rome were marvels of pre-industrial acoustic design. The semicircular seating, the carefully calculated slope, the material of the stage itself, all worked together to project a speaker's voice to thousands of spectators without a single microphone. A performer on the stage of the theater at Epidaurus could be heard clearly in the very back row, every syllable intelligible. The craftsmanship here was an intimate understanding of how sound waves reflect, diffuse, and amplify, knowledge gained through observation and embodied in stone. But the sensory design went far beyond practical amplification. In some sacred spaces, it sought to induce specific states of awareness. On the island of Malta, the hypogeum, a labyrinthine underground temple carved from living rock over 5,000 years ago, holds a profound acoustic mystery. Certain chambers are tuned to specific resonant frequencies. When a person speaks or chants within them, the sound is transformed, amplified, and distorted into an echoing, otherworldly drone that seems to vibrate through your very bones. Researchers suggest these sonic properties were intentional, used in rituals to alter consciousness and create a direct, visceral connection to the spiritual realm. The builders were not just excavating rooms, they were tuning them like the body of a massive stone bell. Visual effects were engineered with equal precision. At the Mayan pyramid of Kukulkan at Chichen Itza, the mastery of solar alignment creates a phenomenon that feels like pure magic. During the spring and autumn equinoxes, the setting sun casts a series of triangular shadows down the stepped northwestern staircase. These shadows connect with stone serpent heads at the base, forming the undulating, illuminated body of a giant feathered serpent that appears to slither down from the heavens to the earth. This is not a vague play of light. It is a meticulously calculated astronomical calendar in stone, a spectacle that merges cosmology, architecture, and public drama into a single, breathtaking moment. The building itself becomes a timekeeper and a myth-maker, its sensory impact timed to the cosmic clock. This holistic design philosophy, where a structure's auditory, visual, and even tactile effects were calculated from the outset, represents a layer of craftsmanship that feels almost alien to our modern approach. Today, we typically build for visual aesthetics and then, as an afterthought, hire an acoustical consultant to fix sound problems with panels and baffles. We control light with blinds and electric switches, separating the environment from the building's innate form. The ancient craft saw these elements as inseparable. The choice of a smooth, reflective stone for a wall was both a visual and an acoustic decision. The orientation of a temple doorway was both a spiritual and a lighting decision. The sensory experience was the purpose. This principle asks us to reconsider what a building is for. Is it merely a container for activity, or can it be an active participant in that activity, shaping emotion, focus, and community through its very form? The whispering gallery, the chanting chamber, the shadow serpent, these are not decorative features. They are the building speaking, singing, and marking time. They remind us that the highest craft engages all of who we are, not just our eyes, but our ears, our sense of wonder, and our place in the rhythm of the cosmos. In silencing these multidimensional conversations, have we built a world that is visually impressive but sensorially quiet? A perfect crack in a marble column is not a mistake, it is a fossilized lesson. To truly understand the ancient builder's mind, we must study not only what survived but what surrendered. The ruins we wander through today, the toppled columns and sunken foundations, are not just monuments to time's victory. They are open-air classrooms holding the most honest records of how these structures interacted with the world. When a Roman aqueduct's arch finally gave way after 8 centuries, the pattern of its collapse spoke volumes about where the stress accumulated, where the mortar had slowly lost its bond, and perhaps where the original calculations met an unexpected force. This forensic approach to failure is one of our most powerful tools for reverse engineering lost knowledge. By meticulously analyzing a ruin, archaeologists and structural engineers can work backwards. They can see the weak point that became a catastrophic fracture. They can measure how a foundation settled unevenly into soft soil, causing walls to lean. Each of these failures reveals the builder's original assumptions about weight, ground stability, and lateral force. It shows us the very edge of their empirical understanding. Take the famous Moai statues of Easter Island. For years, their transportation was a mystery. The pivotal clue did not come from a successful statue standing proudly on its platform. It came from the many that were found abandoned along ancient roads, toppled and broken. The orientation of these fallen giants, the way they lay relative to the path, and the damage on their bases provided critical evidence. Researchers could deduce that they were moved in an upright, rocking motion, and that a sudden loss of control during this delicate process led to their abandonment. The failure preserved a snapshot of the method in action. This perspective shifts how we see ancient engineering. It was not a static set of perfect rules handed down from on high. It was a dynamic, living science of trial and observation. A master builder's knowledge was a library of past outcomes. He knew that building a vault of a certain span with a certain stone had worked in Corinth, but had cracked within a generation in a more seismic region like Anatolia. That failure became a data point, a boundary marker. The next builder, perhaps hearing the story passed down, would adjust his design, maybe thickening the walls or adding buttresses. Their progress was literally built upon the rubble of earlier experiments. This makes their enduring successes even more remarkable. The structures that survived for millennia did so not because the builders knew everything, but because they had learned enough from what had gone wrong before. They had observed how cracks propagated, how soils shifted with the seasons, how wind could fatigue stone over centuries. Their craftsmanship, therefore, was as much about anticipating and mitigating failure as it was about achieving perfection. When we look at a ruin today, we are seeing a dialogue between human ambition and physical law, a conversation that eventually reached a point where one could no longer answer the other. In that silent fracture, we hear the most authentic voice of the ancient craft, a voice that speaks not of invincible triumph, but of hard-won, pragmatic wisdom earned under the relentless pressure of time and gravity. A perfect fracture in marble tells one story, but a digital point cloud can tell 1,000 more. The future of understanding this lost craftsmanship is now being written in lasers and algorithms. High above a dense rainforest canopy, a plane equipped with LiDAR technology sends down millions of light pulses. They pierce through the thick vegetation, mapping the ground beneath with centimeter accuracy, revealing the ghostly footprints of entire cities we never knew existed. This is digital archaeology, and it is revolutionizing our ability to see what was once invisible. Back on the ground, an archaeologist does not simply photograph a weathered stone frieze. She uses a handheld laser scanner, moving it slowly over the surface. The device captures billions of data points, creating a hyper-realistic three-dimensional model that can be rotated, zoomed, and analyzed on a screen. With this digital twin, she can perform magic. She can apply virtual light from any angle, highlighting faint chisel marks and tool signatures that are completely lost to the naked eye in normal sunlight. She can measure the depth and angle of each strike, potentially identifying the specific type of tool used and even the handedness of the craftsman who wielded it centuries ago. This is like recovering the fingerprints of the ancient builder himself. Photogrammetry, the science of making measurements from photographs, allows teams to create detailed models using nothing but a series of overlapping images taken from drones or even smartphones. A crumbling facade, an inaccessible cliff carving, a labyrinthine underground chamber, all can be preserved in perfect digital form before time or the elements claim another piece of their story. The data does not stop at shape. Advanced material analysis using portable X-ray fluorescence scanners can now determine the elemental composition of a stone block or a patch of ancient plaster without taking a single physical sample. We can map where the stone came from, trace the trade routes of materials, and understand the recipes for pigments and binders with a precision that was pure science fiction a generation ago. But perhaps the most powerful application is computational modeling. Engineers can now take these incredibly accurate digital models and place them into virtual stress tests. They can simulate the weight distribution of a Roman aqueduct, applying digital forces to see where the theoretical weak points would be. They can model the flow of seismic waves through an Inca wall to understand exactly how its polygonal joints dissipate energy. They can test the various theories for moving megaliths, calculating the exact forces needed for a rocking motion versus a sledge on rollers, providing a mathematical framework for what was once pure speculation. This technological revival offers a profound new kind of hope. While a laser can never teach your hands the feel of a perfect mortar mix, and a simulation cannot impart the decades of tacit skill held in a master's muscles, these tools are creating something unprecedented, a permanent, shareable archive of empirical evidence. They are giving us the data to reconstruct the methods of the past with a fidelity that old sketches and written descriptions could never achieve. This digital record is immune to the erosion that attacks stone. It can be studied by thousands of researchers across the globe simultaneously, crowdsourcing the puzzle from every angle. The goal is no longer just to guess how it was done, but to build a living, digital library of how it worked. This archive may one day allow us to systematically decode not just the techniques, but the underlying principles of resilience, alignment, and harmony. We are learning to listen to the stones with new ears, and in their silent data, we might finally hear the full conversation. The laser scans and digital models give us the blueprint, but the true blueprint was a way of seeing the world. Stepping back from the precise joints and celestial alignments, we find something even more profound than technique, a complete philosophy for existence. This lost craftsmanship was the physical expression of a pre-industrial worldview, one where humanity did not stand apart from nature, but saw itself as a conscious participant within a vast, interconnected order. To build was to take your place in that ongoing conversation. It was an act of deep participation, requiring a quality we have largely exiled from our modern projects, a reverence for time itself. This was not the fast time of quarterly reports or construction deadlines. It was the slow time of seasons, of generations, of geological patience. A master builder planted trees knowing his grandson would harvest them for beams. He quarried stone with the understanding that his work would be judged by ancestors he would never meet. The drive was not for efficiency or profit in a narrow sense, but for legacy and harmonic integration. The perfect wall was not just strong, it was right. It felt true because it resonated with the same principles seen in a branching river or a spiral galaxy. This worldview framed every decision, from the selection of a stone to the final blessing of a completed temple. The material was not a commodity, but a collaborator with its own spirit and history. The site was not a lot to be cleared, but a unique personality to be understood and honored. The goal was to create something that added to the beauty and stability of the world, a gift to the future that would justify the labor of the present. Reflecting on this invites a quiet but urgent question for our own age. What is the philosophy embedded in our built environment today? Are we creating spaces of disposability designed for replacement, or are we building legacies? Our metrics are often of speed, cost, and square footage, measures that say nothing of beauty, endurance, or spiritual nourishment. We construct towers that may last a century but feel alienated from their place, battling the climate with massive energy inputs rather than dancing with it. The philosophical lens of the ancient builder is perhaps the most valuable artifact we can recover. It is not a call to abandon technology, but to recenter our values. It suggests that true sustainability is not just a checklist of solar panels and recycled materials, though those are important. It is a mindset, a foundational belief that what we make should heal rather than harm, our dialogue with the earth and with time. It asks us to consider the multi-generational story of every object, every building, every city. Recovering this mindset would mean building with a new kind of intention, where efficiency serves longevity, where profit includes the wealth of a healthy community and a healed planet, and where our monuments are not just to power or commerce, but to the enduring human capacity for care. This shift in perspective from seeing the world as a resource to be used to a partner to be honored may be the most enduring structure we could ever hope to create. The philosophy of ancient builders was not an abstract ideal, it was a practical toolkit for survival. Their principles of symbiosis, durability, and holistic design are not locked in the past. They are a blueprint for a more resilient future, waiting to be read with modern eyes. The most direct lesson is a return to material intelligence. This does not mean abandoning steel or glass, but it does ask us to reconsider our first instinct. Before sourcing granite from 3 continents, could we use the stone from a local quarry? Before specifying a complex, energy-intensive cladding system, could we use a regional timber or a rammed earth wall that naturally regulates humidity and temperature? This is not a rejection of progress, but an integration of ancient insight. Using local materials reduces transportation energy, supports regional economies, and creates buildings that look and feel like they belong to their place. The next principle is designing for passive environmental control, a concept our ancestors mastered out of necessity. We can now achieve this with breathtaking precision. Imagine a modern office building oriented to capture the low winter sun, with deep overhangs calculated to block the high summer sun, its thermal mass absorbing heat by day and releasing it at night. Coupled with natural ventilation stacks that draw cool air from shaded courtyards, such a building could slash its energy demands by half or more before a single solar panel is installed. This is not alternative technology. It is fundamental physics, applied with the same site-specific wisdom the ancient builder used, but enhanced by our computational power to model sun paths and airflow with perfect accuracy. For the homeowner, the lesson is beautifully simple. Plant a deciduous tree on the west side of your house. It will shade you in summer and let in light and warmth in winter, a living partnership with the seasons. Perhaps the most profound shift would be to embrace repair and maintenance as a core design virtue, not an annoying afterthought. What if we designed buildings with accessible, understandable systems? What if roofs were meant to be walked on for easy inspection, and walls were designed with sacrificial, replaceable layers? This mindset values the future caretaker as highly as the original architect. It chooses materials that age gracefully and can be fixed with local skills, fostering a culture of stewardship rather than disposal. This leads directly to the 4th lesson, reinvesting in skilled artisanship. In an age of automation, the human hand brings something irreplaceable: the adaptive intelligence to solve unique problems and the care that transforms construction into craft. Supporting stonemasons, master carpenters, and traditional plasterers is not a nostalgic luxury. It is an investment in a living library of tactile knowledge. These artisans are the translators, capable of merging ancient principles with modern needs, creating details that are both beautiful and enduring. We cannot return to bronze chisels, nor should we. But we can choose to use our diamond-tipped saws and computer-controlled mills in service of the same timeless goals: to build in harmony with the earth, to create structures that are meant to be cared for over generations, and to infuse our spaces with a sense of meaning that transcends their mere function. The revival of this integrated mindset, supported by our powerful science, points toward a new era of construction. It would be an era where buildings are not just efficient, but alive to their surroundings, where durability is measured in centuries of service, and where our homes and cities feel less like impositions on the landscape and more like thoughtful contributions to it. The stones of the past ask us a final, compelling question: will we choose to build a world that is only impressive, or one that is truly, deeply wise? The digital models and simulations offer clarity, yet they also illuminate the stubborn shadows where our understanding still fails. For all our technological revival, the ancient world holds onto profound and tantalizing mysteries, puzzles that refuse to be solved with a simple scan or calculation. These are the questions that keep archaeologists and engineers awake at night, the gaps in the story where the lost craftsmanship seems to wink at us from the darkness. They remind us that this is not a closed book, but an active, thrilling field of inquiry. Consider the Serapeum of Saqqara in Egypt, an underground labyrinth not of tombs but of boxes. 24 colossal sarcophagi, each carved from a single block of granite or basalt, weighing between 70 and 100 tons. They are polished to a mirror finish, with corners so sharp and surfaces so flat they could only be the product of extraordinary skill. The real mystery is not just their creation but their placement. These monstrous stone containers are nestled into niches along narrow tunnels, with barely an inch of clearance on either side. How did the builders maneuver these perfect, multi-ton boxes through those tight, subterranean passages and slide them perfectly into their slots? We have theories about ramps and levers, but no method we have tested recreates the feat with the same elegant precision. The logistics feel almost impossible, a silent demonstration of a technique we have yet to fully comprehend. Then there are the vitrified forts of Scotland, ancient hilltop strongholds where sections of the stone walls appear to have been melted into a crude, glassy slag. This vitrification requires temperatures exceeding 1,000 degrees Celsius, far beyond what a simple timber fire should achieve. Was this the result of a catastrophic attack where an intense, sustained siege fire somehow fused the stone? Or was it a deliberate defensive technique, a way of strengthening the walls that we have completely forgotten? The evidence is contradictory, and the full story remains locked within those bizarre, glazed stones. These are not mere historical footnotes, they are direct challenges to our narrative of the past. Each one represents a boundary line, a place where our current explanations run out. They force us to consider possibilities that stretch the imagination. Some researchers, for instance, looking at legends from multiple cultures that speak of stones being moved by sound or by the voice of priests, wonder if there is a kernel of truth buried in the myth. Could certain resonant frequencies, applied with exact knowledge, reduce friction or make massive weights temporarily easier to maneuver? It sounds like fantasy, yet the acoustic mastery displayed in places like Malta's hypogeum proves these cultures understood the physical power of sound in profound ways. While we lack proof for sonic levitation, the very fact that we are pushed to consider such ideas shows how far these mysteries can bend our thinking. These enduring questions are the lifeblood of discovery. They are the whispers that invite a new generation of explorers, engineers, and dreamers to listen more closely. They prove that the dialogue with the ancient builders is not over. We are still asking questions, and sometimes, in the quiet of a desert tomb or on a windswept Scottish hill, we can almost hear the stones preparing an answer we have not yet learned how to hear. These silent conversations with stone and starlight leave us with a quiet, resonant echo. From the pyramids of Giza to the swaying pagodas of Japan, we have traced not a single lost tool, but an entire lost language for building. It was a language spoken in the ringing tone of a perfect stone, in the celestial alignment of a temple doorway, and in the patient, generational rhythm of a master teaching his apprentice. This lost craftsmanship was a symphony, one where deep material knowledge formed the foundation, sacred geometry wrote the melody, and a profound harmony with the environment provided the enduring rhythm. These structures stand not by luck but by design, as monumental testaments to a holistic vision. Their builders saw no separation between the spiritual and the structural, between the needs of the present and the responsibility to the future. They built with a patience we have forgotten, understanding that true resilience is not created in a single lifetime, but is a gift carefully crafted for those you will never meet. We may never fully recover the master's touch, that tacit wisdom held in the hands and the eyes. We cannot unlearn our clocks and return to an age of slow stone. Yet their legacy is not a relic to be admired and left behind. It is a profound challenge cast across the centuries. It asks us to look at our own world of glass and steel and consider the philosophy embedded within it. Are we building for disposability or for legacy? Are we battling our environment or learning to build in partnership with it? The silent stones of antiquity are a call to action, urging us to build with greater intention, with deeper sustainability, and with a renewed respect for the long arc of time. They remind us that every wall we raise, every space we create, is a message to the future. What will our message be? What will we create that is so thoughtfully made, so harmoniously conceived, that it will still have a story to tell 1,000 years from now? We would love to hear which ancient mystery resonates most with you. Does the seamless joinery of the Inca walls capture your imagination, or is it the self-healing concrete of the Romans? Share your thoughts in the comments below, and if you have been captivated by these echoes of lost genius, subscribe to continue unraveling the profound secrets of our past.